So, using Ampere's law, we derived a magnetic field for various kinds of current distributions, and the last one that we derived was a solenoid, long solenoid. And if you have a long solenoid and then you, if it is flexible and if you can turn and then join here, that makes a toroid. So, essentially toroid is like you have a tube, or say your cycle tube or tire tube. On that, if you wind the turns, that becomes a toroid. So, if I try to draw the diagram here, it will be something like this. This is the inner side of the tube and this is outer side of the tube. So, here is this is the tube, this is the tube, and this part is vacant, and of course, and here you wind the turns, here you wind the turns like this. Here you wind the turns, and of course, the current comes and then current goes like this. So, everywhere you have a current, in every turn you have a current, in every turn you have a current. So, the current goes this way, this way, this way, this way, this way, this way, then it comes here. Now, if this is the current, and then the number of turns per unit length is now one can define, but you can see that on the inner side, the turns have to be closer as compared to outer side. So, number of turns per unit length here will be different than number of turns here. Here it will be more compact, because in less periphery, in less length, the same number of turns are to be adjusted, and here the number of turns per unit length will be smaller. So, because of this, if I take this as the origin, and then our z axis is perpendicular to the board, and this is, if I am here somewhere here, then this will be our S, this length is S, and this direction is S cap, and phi cap is, of course, this is phi cap, and this is Z cap. So, our axis system is somewhat different from the solenoid. In the solenoid, we had this kind of structure, and then we said that this central axis is the Z axis. In this particular case, if I take the central line, that is not a straight line, it will be a circle, and therefore, we cannot take this as the Z axis. Right. Here this is the Z axis going through the centers of the turns, but then here centers of the turns, if I take, it is making a circle. So, the axes are to be chosen in somewhat different fashion, and this will be our Z axis, origin will be here, and then this will be Z axis, and then wherever you are normal, that distance is S, and this is S cap, and then perpendicular is phi cap. If you are here, then this is S, this is S, this is S cap, and this is phi cap, this direction is phi cap, like that. So, that is our system. Now, here you know that if you have a solenoid and then you have turns, you have currents in each turn, then the magnetic field inside is of this kind. So, here you will expect that if the currents are going in the turns, the magnetic field will be of this kind, here in this direction, here in this direction, in phi cap direction, and that is true. That is true. The magnetic field is like phi cap direction. So, B is B phi cap. But then in this case we said that the magnetic field is uniform inside everywhere. Inside the solenoid, the magnetic field is uniform. It is in the Z direction, and then the value is B equal to mu naught Ni k cap. This was the magnetic field. So, the magnitude here is mu naught Ni, and this is constant whether you are close to the axis, away from the axis, as long as you are inside that solenoid, then the magnetic field is given by this constant value in k cap direction. Now, here since n in the case of toroid, this n itself is not a constant, inner side n is more, outer side n is less, and everywhere in between if you take, it will be somewhere in between. Therefore, you expect that there can be S dependence of magnetic field. Magnetic field here and magnetic field here may be different from each other. Here S is different, here S is different. So, the magnetic field at this point where S is small and magnetic field at this point where S is large, remember this is our S, this is our S. So, since n is varying, n is not constant, you expect that the magnetic field may have a S dependence, not S direction, but S dependence. The magnetic field is in phi cap direction, but then the magnitude here may be greater because you have more number of turns here, and here it may be smaller. So, that we want to derive, using this Ampere's law. So, what we do for that, inside these turns you make a circle, remember for Ampere's law you need a closed curve, So, if this circle is at a distance s, the radius of the circle is s, let us say the radius of the circle is s. So, I want the magnetic field here, phi symmetry is there, whatever is the magnetic field here, magnitude, the same magnitude will be here, the same magnitude will be here, the same magnitude will be here, the same magnitude will be here. There is no difference between this point and this point, this point and this point, there is no difference. But this point and this point, yes, there is a difference, more number of turns per unit time this side, less number of turns per unit length this side. So, this and this you can distinguish, but this and this you cannot, and therefore, it is in phi cap direction, but then the magnitude is to be calculated. So, on this we will be using Ampere's law, and that is B dot dl on the closed curve should be equal to mu naught times I enclosed. What is this I enclosed? Once again, the total current that passes through the area enclosed by the closed curve. Here you have a closed curve, this B dot dl, you take a circle and then say that okay, this is dl, here this is dl, here this is dl, here this is dl. So, the dl is changing everywhere like this, and then up to here you have to do that. So, this is a closed curve on which you are varying this dl, and on that closed curve you have to do this integration, and that same closed curve, the area bounded by that same closed curve comes here. Through that area how much current is crossing, that will come here. So, let me do it with a model that we have created for convenience. This is our toroid. Okay. So, this is a tube, actually a cycle tube, bicycle tire rather, and then on that we have wrapped this rope, and you assume that each turn carries a current, each turn carries a current. So, the current is going this way, comes this side, then goes this side, then comes this side, goes this side, and that way the entire this loop is this toroid is carrying this current on the circumference. Now, what we will be doing is, where is our Amperian curve? This curve, this curve, this curve here. It is going in between, all right, in between this inner periphery and outer periphery. So, this is inner periphery, right, this is inner periphery, this is outer periphery. In between this circle is going. Suppose this is z axis, then from here at a distance s, the inner periphery is at some distance, say S1, the outer periphery is at some distance S2, inner radius is S1, outer radius is S2. In between that, from the inside, this circle is passing like that, and then the area enclosed by that circle, this big circle. So, this whole area will be there, and at the same time inside that toroid also up to that S, this is S1, this is S2, and the circle is at S. So, up to that S, this disc will be there. So, look at this situation, if it helps, that I am showing that disc, and remember it is not ending here, although in my model it is ending here because I cannot penetrate, but the periphery of this disc is going through this inside of the toroid up to a distance of S from the center. This is our z axis, and then this is S1, and our this disc is going up to distance S because our circle is there, and it is the area bounded by the circle through which I have to see the current. So, look at this disc now, which is penetrating and going inside. Now, this turn here, this particular turn here is going through this disc. The current is coming here, and then the current has to go down, but then the disc is here and it has to cross the disc, right. This disc is extended up to that distance S, remember. So, this turn is going through that disc, that area enclosed by the closed curve, and therefore, it must be counted in this I enclosed. Inside this circle, the current is crossing that area. This turn, every turn in the entire toroid, every turn is crossing that area. So, if the total number of turns is capital N, not per unit length, total number of turns is capital N, and each turn carries a current I, how much current is crossing this disc? This is capital N into I, because every turn on the toroid is going through this, and therefore, this I enclosed is mu naught into capital N into I, where capital N is the total number of turns. And this side is simple, this B is B phi cap, and this dl, this vector, this is also phi cap direction. So, it is dl phi cap, and then the integration, phi cap dot phi cap is 1. So, it is B phi into dl, B phi into dl. Now, at a given S, here you are integrating over that dl. So, whether you are here or here or here or here or here, the magnitude of the magnetic field is same. It will vary if you change that S, because then if you are close to the inner periphery, more number of turns, expected more magnetic field. If you are going away, then expected magnetic field will decrease. So, this way it will change, but this way it will not change. This point, they are all equivalent, and therefore, B phi is constant, and hence you can write this as B phi you can take out, and it is dl here, and that is B phi into 2 pi s. All this dl, you are adding all this dl, magnitude. So, that will be 2 pi s, because radius is s, periphery is 2 pi s. So, that is the left hand side. So, what is it now? B phi into 2 pi s, B phi into 2 pi s is equal to B phi into 2 pi s, that is equal to, this was RHS and LHS, this is LHS and RHS is this. mu naught capital N I. So, it is mu naught capital N I, right, and therefore, B phi is equal to mu naught capital N I divided by 2 pi s, and B is equal to mu naught N I divided by 2 pi s phi cap. Okay, so, as expected, if S is small, that means we are close to the inner periphery, this is S, then the magnetic field is larger, it is in the denominator. If S is increased, you are going away towards the outer periphery, then this S is increased and the magnetic field is decreased. So, this kind of toroidal magnetic field is also quite important in fusion research, nuclear fusion research. People are trying very hard to commercially viable to produce nuclear fusion and energy from nuclear fusion which is commercially viable. So, all those experiments are going on, and this geometry is used to confine that hot plasma inside, and so on, so on. That is a separate topic. Okay, so, that is all I have to do with calculation of magnetic field using Ampere's law. Now, the next thing is, if you have this magnetic field because of certain currents, then there are certain boundary conditions. In electrostatics also we have boundary conditions on electric field. In magnetostatics we have boundary conditions on magnetic field. If you have a surface and if there is a current on the surface, as we had seen, we have solved that problem. So, if you have a surface of any shape and you take some small part there, and just outside this surface on one side and on the other side, how do magnetic field components compare? So, that is known as boundary conditions. So, let me show the boundary conditions on magnetic field if there is a surface and which carries a current. So, what I will again I will be showing you a model, but let us first do some drawing here. Suppose here is a surface, not necessarily plane surface, but some point here, and I am interested just here. So, this is a horizontal surface, I go slightly up and I go slightly down. So, one side of the surface and other side of the surface, just on this side, just on that side, we take 2 points. So, we take a point out here and we take a point out here. Remember this is up and this is down, and this point is on this xy plane. Okay. So, let me do it on a model that will be easier to understand this 3-dimensional picture. And here it is, this is a surface, this is a surface, and these arrows that you see, these denote current. So, current is going on this surface like this, in this direction. Now, on one side of this surface we have taken a point here, and on the other side of the surface we have taken a point here. So, we first take 2 points, look at my fingers. So, this represents one point and this represents another point. One point is on one side of the surface, other point is on the other side of the surface. So, this is the geometry. Then with this as the point, including this point, we construct a plane surface here, all right, and here also we construct a plane surface here. So, here the surface is like this, here the surface is like this, and then we join and make a cylinder. Half the cylinder is above the surface, half the cylinder is below the surface. Okay. If you look at that YZ plane, if I say that my plane is here, what I am showing on the board is just this Y, and this is Z perpendicular to the plane. The plane is like this and the current is coming like this. I denote the current by these dots like this. Then I can say that okay fine, here is one point, here is one point, this is above, this is below. Here I take a circle or an area including this, here I take a circle and area including this, and then here is the cylinder. So, you can see on this model, this is the cylinder, this blue thing is a cylinder, from here up to here, this is one cylinder. Now, this closed surface, this flat surface plus this flat surface and this curved surface and this curved surface, this closed surface of the cylinder, on this closed surface we will apply our divergence equation. Divergence of B is 0, remember, and this gives me B dot dA. B dot dA on a closed surface is 0. B dot dA on a closed surface is 0, and on this cylindrical surface we will be considering this quantity B dot dA. What is the direction of dA here? What is the direction of dA here? This direction will be outward normal, and that is this direction. Okay. Let us call this side as side 1. This is side 1. So, let me say that this is side 1. So, this is side 1 and this side is side 2. So, in side 1, this outward normal, this is the direction of this dA vector. So, this B dot dA, so B dot dA will be, we call it dA n cap. Okay, let me write it this way. This dA vector is dA n cap, and what is n cap? N cap is the normal to this surface, because this area is parallel to this surface. So, it is perpendicular, it is normal to the surface and going inside one, that is our n cap. And then B and then dot n cap. What is this? What is this? B dot n cap. This is component of B in n cap direction. Unit vector, n cap is the unit vector. So, B dot n cap will be just B into cos theta. So, that is the component of B in n cap direction, and since I am calling it side 1, so let me write it B1. So, we write it B1. This is on the closed surface. Now, on this surface I am trying to now write this B dot dA on this surface, and this is side 1. So, we will write this part of this on this surface, it will be B1 n. N means normal component, B1 n, n means normal component, and 1 because I am talking of this part. So, this is this part into this area delta A. What I am doing? I am trying to evaluate this integration. The integration has to be evaluated at the closed surface. Here the closed surface has several parts. One part is this, another part is the plane surface behind, and then the curved surface of the cylinder. Okay. So, one part I have done. Now, go to the back side. We will still take our n cap in the original direction, this n cap. In side 1 we are drawing the normal, and that is n cap. So, that I will be calling n cap. So, what will be the B dot dA there? It will be this dA is now in this side, dA vector is in this side, dA vector is in minus n cap direction. So, for this part we will say that this dA vector for the second part, behind. So, this is our first part, this was our first part that we wrote. First part means inside one flat surface, and the second part is this behind this part here, this is side 1, this is side 2, inside to the flat surface once again, and here n cap is here, dA vector is outward normal. Therefore, we will say that this dA vector is dA and minus n cap, and therefore, B dot dA will be B dot minus here, n cap here, and then this dA here, and this will be minus B, let me write it 2 second side. So, B 2 and then n dA minus, because I am taking the component in the same n cap direction, and therefore, since dA vector is opposite, that is why this minus is coming, and this B 2 dA is this. So, here it will be or delta A. Now, this dA is fine, but this whole thing when I do on this entire surface which is delta A. So, this will be B 2 n delta A with a negative sign. So, I put minus here, okay. And then we have curved surface, So, what is the B dot dA here? Since I am talking of just on one side and just on the other side, this point P is taken very close to the surface, just outside, just other side, and therefore, this height is negligible. Total surface area of this curved surface is negligible. How much is this curved surface area of cylinder? It is 2 pi r, the periphery, and then multiplied by this height of the cylinder. Since height of the cylinder is going to 0, I am talking of just this side and just that side, the total surface area itself is getting 0, and if the surface area itself is getting 0, then this B dot dA on the curved surface will be 0, because curved surface area itself is going to 0, and therefore, that is all, plus 0, curved surface plus 0. So, that is we have calculated this closed surface integration here, and that is this much, and right hand side is 0. So, this is 0. So, what does this tell? It tells B 1 n is equal to B 2 n. Independent of the current is there, and then we are asking what is the perpendicular component of the magnetic field here, and what is the perpendicular, the same in the same direction, what is the magnetic field component here, and they are coming to be the same. So, we say that the normal component of the magnetic field across a surface, as you cross this surface, the normal component of magnetic field does not change. So, this is, it tells, this is one boundary condition, normal component across a surface does not change, remains same. Even if you have a current on the surface, even then across the surface the normal component will not change. Okay. So, in the next lecture we will be talking of the tangential component of the magnetic field. If I have this surface and there is a current, and this is the surface on which I am taking the current, it can be part of a big surface, right, and that big surface may be weird. But then I am talking of just some point, and since I am very close to that, what is happening here is not important, what is here, that is important, the direction of current. So, tangential can be in many directions. This is also tangent to the surface, this is also tangent to the surface, this is also tangent to the surface. There are many tangential directions. So, we will see how to handle that, and we will compare the tangential direction magnetic field component in tangential direction across the surface this side and that side.